Hi, so today I'm going to be talking to you about continuity. So the two criteria for a function to be continuous is that the limit of x approaching a of f of x exists, and the limit of x approaching a of f of x is equal to f of a. There are two types of discontinuities, removable discontinuities and non-removable discontinuities. Removable discontinuities include holes, and non-removable discontinuities include vertical asymptotes. Common mistakes for determining continuity usually come from a person forgetting the criteria for continuity, that the limit of x approaching a of f of x must exist, and that limit must equal to f of a. For example, if you look at this graph at x equals 4, the limit exists, but the limit of x approaching 4 does not equal to f of 4. Also, the student might confuse continuity, the existence of the limit, and differentiability because the criteria for each of these are different. So for the first example problem, we will be looking at this graph and find where is the function discontinuous. So if we were to look at this graph, we could see that at x equals -4 and x equals 2, the limits do not exist. Therefore, the function is discontinuous. And at x equals 4, there is a removable discontinuity, so it is also discontinuous there. But if we were to solve it using limits, we could solve that limit of x's approaching -4 from the left side of f of x is equal to 3, and from the right side is equal to -2. Therefore, the limit of x approaching -4 of f of x does not exist, and it's not continuous at x equals -4. We would do the same at 2 and find that limit of x approaching 2 of f of x does not exist, therefore it's not continuous at x equals 2. And then at x equals 4, we find that the limit of x approaching 4 of f of x does exist, and it equals 2, but f of 4 does not exist, therefore it is not continuous at x equals 4. When I am solving for continuity on graphs, I like to think of it as when is my pencil leaving the paper to continue the function. So at -4, 2, and 4, my pencil is leaving the paper because I have to jump to another position on the graph to continue the function. So for the second example problem, we will determine when r of t is equal to 8t over t squared minus 9t minus 1 is discontinuous. So because r of t is a rational expression, if it is dividing by 0, it will be discontinuous. So we set t squared minus 9t minus 1, or the denominator, equal to 0. And then we solve for t, and we get 9 plus or minus root 85 over 2. So r of t is discontinuous when t is equal to 9 plus or minus root 85 over 2. So for this third example problem, we will use the intermediate value theorem to show that 25 minus 8x squared minus x cubed equals 0 has at least one real root in the interval -2, 4. So the intermediate value theorem states that if f is continuous on the closed interval ab, and k is any number between f of a and f of b, then there is at least one real number c in AB such that f of c is equal to k. So we're making f of x equal to 25 minus 8x squared minus x cubed, and m will be equal to 0. So the problem is asking us to show that there is a c in -2, 4, so that f of c is equal to 0, which is equal to m. So we first need to make sure that the criteria of the intermediate value theorem are met. So f of x is a polynomial, therefore it is continuous on -∞ to infinity, and also continuous on our interval -2, 4. Then we want to verify that m is between our function values at the endpoints of the interval. So we plug in -2 and 4 into our equation and get f of -2 is equal to 1, and f of 4 is equal to -167. So -167 is less than 0, which is less than 1. So by the intermediate value theorem, there must be a number c such that -2 is less than c, which is less than 4, and f of c is equal to 0. So for the fourth example problem, we want to find a such that f of x is continuous at x equals 2. So first we find the limit of x approaching 2 from the left side of f of x, which is equal to the limit of x approaching 2 from the left side of a plus x, which is equal to a plus 2. And we do the same for the right side, and that equals 5. Then we set a plus 2 equal to 5 because a function is continuous when the limit exists, and the limit exists when the left side is equal to the right side. So we set a plus 2 is equal to 5 and get a is equal to 3. The fifth example problem is a multiple choice problem, and we want to find if f is continuous at x equals -1 and x equals 1. So we're going to find the limit of x approaching -1, and we do that by finding the left and the right hand side limits, and we get -3 and 2 for the left side and right side respectively. Therefore, it is not continuous at x equals -1. When we do the same thing for x equals 1, we get that the limit of x approaching 1 is equal to 2. And we also find that f of 1 is equal to 2 because we plug in 1 to the bottom equation of the piecewise function, and so we find that f of 1 is equal to 2, which is equal to the limit of x approaching 1. Therefore, the function is continuous at x equals 1. And we see that our answer is C, because f is continuous everywhere except x equals -1. Thank you so much for watching this video, and I hope that it helped you.